We had the zeroth law of thermodynamics, which was you can measure the temperature, and if you measure the temperature here and you measure the temperature there, and they're the same, they're the same. But the first law of thermodynamics comes from the conservation of energy, because thermal energy is energy, and it can't be created or destroyed. That's what it says. It cannot be created nor destroyed. You can increase thermal energy within a system by heating it up or by doing work in that system somehow. You can start to move the particles in there. Yeah. I don't know if you've ever done this before with like a bike pump or a syringe, but if you have if you have a syringe or a bike pump and you plug up the end of the the hose, and then you start trying to pump, you're just like pretty much compressing air, and the tube actually gets hot. You're creating thermal energy. You're making those particles bounce around, and it actually gets hot. It gets warmer, not hot, but that's an example of taking the mechanical energy that you have, moving up and down, and then transferring it into heat. Same with rubbing your hands together. It's creating thermal energy. I don't really know why they have this example. That's silly. And maybe because you're doing work. You're doing work, and it's transferred into thermal energy. There we go. That's probably why. The second law of thermodynamics says that thermal energy flows from hot to cold. In the PowerPoint, this is actually just an animation, so it's not just a shot of tequila or something. There was ice, and then it melts. So this is water in there, I'm assuming. But anyway, thermal energy flows from hot to cold. So if you put ice in a glass of water, the thermal energy you may think is going, oh yeah, is this going from the ice cube to the water? But no, the water is actually heating up the ice cube, right? And then it turns into more water. So the thermal energy is transferred from the water to the ice. In that specific example, when you touch a frozen pizza with your hand, the thermal energy flows from your hand to the pizza, from hot to cold, because your hand, hopefully, is warmer than a frozen pizza, unless you're dead and also frozen. Well, when you touch a cooked pizza with your hand, the thermal energy flows in which direction? If it's still warm, if you feel that it's warm, then the thermal energy is flowing from the pizza to your hand. Who eats pizza that close together? Give each other some space. Jeez, it's disgusting. The second law of thermodynamics says that entropy will either increase or remain the same, but we have to know what entropy is in order to understand that. Entropy is the measure of how evenly distributed heat is within a system. Another way to think of entropy is a measure of the amount of energy which is unavailable to do work. So if something's nice and organized, like the wood, the molecules are all nice and lined up, they're still able to do some work. But if I don't know how well that works out, that analogy. I guess you can think of it as entropy. If everything's all in order, then it has a low entropy. If everything's all heated up and the particles are bouncing around, or the molecules are bouncing around, there's a lot of disorder. That's high entropy. We're not going to be dealing too much with talking about entropy, but it is part of the second law of thermodynamics, and we are talking about thermodynamics, so we talk about it. Well, I already talked about the thermal convection. Here's another example. It is the transfer of thermal energy through movement of fluid. We already talked about that. When a fluid is heated, it expands, more or less dense. Boiler. No, who has that anymore? Actually, when you go to college, you will probably have something like this, because your apartments will be old. So this would heat up. This would heat up, and then the air at the bottom of the room would get warm, and then it would rise, and then cooler air would fall, and then get heated up by this, and then it would just circulate and then heat up the room. That's what it does. That's how it heats the room. Or if you have like a space heater, same idea. I dislike this example that they gave you because convection, we just said, was through the movement of fluid. And then it talks, the PowerPoint talks about soup, which I would assume is a fluid, but they're not talking about the transfer of like the heat through the soup. It's talking about something else. So they're saying conduction is the transfer of thermal energy within an object or between objects from molecule to molecule. It means they're touching. So when it says a metal spoon placed in a hot cup of soup will feel warm to your hand, the conduction is happening from the spoon. Well, it's happening from the soup to the spoon to your hand. That's what they're talking about. They're not talking about the heat transfer within the soup. That would be like heat transfer within the soup. That would be convection because it is a fluid. So yeah, that's conduction by touching. Not touching. That's from Arrested Development. We will be doing some calculations for thermal energy transfer. We will be using Q equals, some people say MCAT, where Q is the energy transfer in joules. You measure energy in joules. M is the mass of the material that we're talking about for the energy transfer. C is the specific heat capacity of the material. This is specific to each material. So specific heat is the actual definition is, I think, the energy that it takes to raise a certain amount of this material, of whatever material you're talking about, 1 degree Celsius. But the way you can think of it is like maybe like how difficult it is to heat up. If it takes a lot of energy to heat it up, then it has a high specific heat. If it doesn't take that much energy to heat it up, it has a low specific heat. If it also, another way of thinking about or around it, is if something has a high specific heat, it retains heat well. It holds heat well. So that's sometimes why it's called specific heat capacity, because it can hold that thermal energy well as also. So that's maybe I'll write that down. So a high specific heat means it takes a lot of energy to heat it up, to heat whatever substance you're talking about, whatever material. And then the delta T is just the change in temperature, the starting temperature, the difference between the starting temperature and the final temperature. We have one more slide, and I'm going to end the video. Okay. Here we have a couple more equations. P is the P is the rate of energy transfer. That's in watts. It's just the joules divided by time. That's how you get watts. Remember, watts are just joule. 1 joule. 1 watt is 1 joule per second, I think. Q, is the energy transfer in joules. Delta T is the change of time. K is the thermal conductivity. That all depends on the material that you have and like the dimensions of the material. So this is a characteristic of whatever material you're talking about. A is the area of the thermal conductivity, so like the area where the heat is being applied or transferred or whatever. L is the thickness, and yeah, everything else is pretty much self-explanatory. We'll get to these later. I'm done.